Hello class, so for today's discussion here in Statics of Rigid Bodies, we are now down to our sixth lesson, which is about resultant of non-concurrent force system. So this will be the discussion of our last topic about solving the resultant of force systems. So for this topic, these are the following intended learning outcomes. So students must be able to compute resultant of non-concurrent force system, and students must be able to locate and draw the resultant of non-concurrent force system. So before we proceed to our discussion, you will answer first these problems for bonus points. Okay, so referring to the figure for questions 1 to 3, here's the problem. If Ry is equal to 250 Newton, Rx equal to negative 190 Newton, and Ix equal to 5 meters, determine the moment about point O. The second question is, if the moment at point O is negative 200 pound-inch and distance d is 3 feet, determine the resultant R. And for the last question, number 3, if Ry is equal to 10 kips, Rx equal to negative 7 kips, and Ix is equal to 7 feet, determine the distance d. So for every problem, you can receive 2 points. Okay, so maximum of 2 points for every student. So you just have to comment the your name, your section, and the item that you answered and your answer. So don't forget to include the unit of your answer. So the first student to give or to comment here the correct answer, the right answer, okay, will receive the bonus point. Okay, I hope you receive the bonus points, class. Recalling non-concurrent force systems, these are force systems wherein the forces don't meet at one point. So these are force systems that are neither concurrent nor parallel. So for resultant of non-concurrent force systems, to solve for the magnitude of the resultant, that will just be r is equal to square root of rx squared plus ry squared, wherein rx, that will be the horizontal component of the resultant, and it can be solved by summing up or by the summation of all the horizontal components of the forces in the system. Okay, and Ry, that will be the vertical component of the resultant, and it can be solved by the summation of all the vertical components of the forces in the system. Now, for the inclination of the resultant with respect to x-axis, we can use tangent of theta x equals to ry over rx, wherein ry, that is the vertical component of the resultant, and rx, that is the horizontal component of the resultant. So to solve for theta x, that will just be arctangent of ry over rx. Now, for the summation of vertical and horizontal components of forces, we can use the sign convention that if the force is directed to the right, in the summation, that will be positive for horizontal component. Okay, but if it's directed to the left, that will be negative in our summation. Now, for if the force is directed upward, that will be positive in the summation for vertical components, and if it's directed downward, that will be negative. So let's say we have here this non-concurrent force system. So this is non-concurrent since all the forces here don't meet at one point. So these are neither, this force system is neither concurrent nor parallel. So this is a non-concurrent force system. So for this non-concurrent force system, if we solve for its resultant, so let's say the resultant will be located somewhere here. Okay, so this will be the resultant R, and this direction, it will depend on your Rx, or the horizontal component of your resultant, and Ry, which is the vertical component of your resultant. So in this case, if your horizontal component of the resultant is negative in your summation, that will be to the left, no? Its direction will be to the left, okay? And if your Ry is directed upward, okay, so if your summation here is positive, meaning to say your Ry is directed upward. So the vertical component of the resultant is upward and to the left. Okay, so let's say this is the direction of your resultant R. So your theta x will be located here. Okay, so this will be the inclination of this resultant from the horizontal. Okay, so we solved it using tangent theta x equal to ry over rx. Now, also one of the most frequently asked questions for this topic is the distance d, okay, of your resultant from a specific point, let's say from point O. Okay, so this is one of frequently asked questions here. Okay, the distance d or the moment arm of this resultant r at about a specific point, let's say at point O. So this will be, we will solve this, no? So to solve for this perpendicular distance d of the resultant from point O, we are going to use the concept of Varignon's theorem. Okay, so we will use m sub O, that will be equal to summation of m sub O is equal to Rd is equal to summation of Fd. So meaning to say, if we are asked here to solve for this perpendicular distance d, no, of the resultant from that resultant, no, from the line of action of that resultant to point O, we are going to take moment about point O. Okay, and that moment, okay, at point O, that will be equal to the moment of all the forces, okay, that have a moment about point O. Okay, and that is also equivalent to the moment of the resultant. Okay, so the moment of the resultant about that point will be R times D. Okay, and that is also equivalent to the summation, okay, of the moment, okay, of the component forces of the resultant. Okay, so again, your RD, that will be the moment, okay, of your resultant about point O. And summation of FD, that can be either summation of the moment of component forces. So the component forces of the resultant are these forces, let's say F1, F2, F3, F4. So the moment of these forces, that will also be equivalent, okay, that will also be equivalent to the moment of the resultant, okay, at that same point, no? So it can also be the summation of the moment of the horizontal and vertical component of the resultant about point O. So your resultant R, okay, it has a vertical and horizontal component, right? So the moment of those horizontal and vertical component about point O will also be equal to the moment of the resultant. Okay, so your summation of FD here is either this, again, the summation of the moment of component forces F1, F2, and so on, or the summation of the moment of horizontal and vertical component of the resultant about that same point O. Okay, so let us solve sample problem number 1. The rectangular framework shown in the slide is subjected to the indicated non-concurrent system of forces. Determine the magnitude and direction of the resultant. Also, its moment arm relative to the origin O. So this is our force system given here. Okay, so these forces are non-concurrent, okay, or this force system is non-concurrent because the forces here, okay, don't meet at a common point. Okay, and this force system is also not a parallel force system. So meaning to say this is a non-concurrent force system. So we are going to solve this. Okay, so let's start solving this. So for this problem, we are asked you to solve for the resultant. So your resultant, it must include the magnitude, the direction, and inclination or theta x. We are also asked you to solve for the moment arm of the resultant from point O. So the moment arm here is the perpendicular distance d, okay, of the resultant from the specified point, which is point O. Okay, so let's start solving this. Okay, so to solve for the resultant, we must first solve for Rx and Ry. Okay, so for Rx, that will just be equal to the summation of all the horizontal components of the forces in the system. So we have here this assumption that for forces that are directed to the right, they will be positive. So let's start solving for Rx. Okay, so let's start with this 20 Newton force. So this is 30 degrees from the horizontal. Okay, so its horizontal component will be 20 cosine 30 degrees. Okay, so since it is directed to the right, it will be positive here in our summation. Now, for this 100 Newton force, this is inclined 45 degrees from the horizontal, and its horizontal component will be 100 cosine 45 degrees. Okay, and since it is directed to the left, okay, it will be negative here. Now, for our 60 Newton force, since this is already a horizontal force, okay, so this will be directly included in our summation. So, since this is directed to the right, it will be positive in our summation. Okay, now for this 100 Newton force, this is 60 degrees from the horizontal. Okay, so its horizontal component will be 100 cosine 60 degrees. Okay, so, and since it is directed to the left, it will be negative here. Now solving for this 30 Newton, so since it is a vertical force, okay, so it will not be included in our summation for horizontal components. Okay, so this will now be our Rx. So solving for this, so let's input this in our calculator. So this will be 20 cosine 30 degrees minus 100 cosine 45 degrees plus 60 minus 100 cosine 60 degrees. Okay, so see to it that your calculator is in degree mode since our angles here are in degrees. Okay, so our Rx will be negative 43.39 newtons. So you can notice here that it is negative. So meaning to say, if it is negative, since our assumption is positive for forces that are directed to the right, so meaning to say our Rx, okay, is actually directed to the left. Okay, so our Rx is 43.39 newton, okay, to the left. Okay, so that will be the value of our Rx or the horizontal component of our resultant. Now, proceeding to our Ry, okay, so that will just be the summation, okay, of the vertical components of the forces, okay, in our system. Okay, so let's start solving this. So our assumption here will be positive for forces that are directed upward. Okay, so solving for Ry, so let's start with this 20 Newton force. Okay, so since this is 30 degrees from the horizontal, its vertical component will be 20 sine 30 degrees. And since it is directed upward, so this will be positive here in our summation. Okay, now for this 100 Newton force, its vertical component will be 100 sine 45 degrees. Okay, this will be that value, no? And since it is directed upward, it will be positive in our summation. That's why it's positive here. Now, for this 30 Newton force, since this is a vertical force already, okay, we can directly include this in our summation. And since it is directed downward, it will be negative in our summation. So this will be negative 30. Now, for this 100 Newton force, its vertical component will be 100 sine 60 degrees. And since it is directed downward, it will be negative in our summation. Now, for your 60 Newton force, so this is a horizontal force, okay? So it will not be included in the summation, okay, of vertical components, okay, of forces. So solving now for our Ry, okay, so let's input this in our calculator. So this will just be 20 sine 30 degrees plus 100 sine 45 degrees minus 30 minus 100 sine 60. So again, your calculator should be in degree mode since our angles here are in degrees. Okay, so the answer for this will be negative 35.89 newtons. So you can also notice here that our sign here is negative. So meaning to say your Ry is actually directed downward. Okay, so our Ry is 35.89 Newton downward. Okay, so since we have solved for the value of Rx and Ry, or the horizontal and vertical component of our resultant R, we can now solve for our resultant R. So that will just be square root of Rx squared plus Ry squared. So that will just be square root of 43.39 Newton squared plus 35.89 Newton squared. So that will give you 56.31. So let's input that in our calculator. So again, that is square root of 43.39 squared plus 35.89 squared. So that will be 56.31 Newton. So that will be the magnitude of our resultant. Now, for the direction of our resultant, so our Rx is to the left and our Ry is downward. So meaning to say the direction of our resultant will be downward to the left. So this will be our resultant and its direction. Now, for the inclination or for theta x, that will just be from tangent theta x, okay, is equal to ry over rx. So solving for theta x, that will just be arctangent of ry over rx. Okay, so let's input that in our calculator. Arctangent of ry, which is negative 35.89, over rx, which is 43 or negative 43.39. So that will give you 39.60 degrees. Okay, so this will be the theta x or the inclination of the resultant r, okay, from the horizontal. So this will be the answer for this. Now, we are also asked here to solve for the moment arm, okay, of the resultant from point O. No? So, we can have here tentative locations of the resultant, okay? So, we can assume, okay, where we can find our resultant. But this will just be tentative since we are not yet sure, okay, of the location of the resultant. So, this will be the tentative location. So, our resultant are, okay, so that will be theta x from the horizontal. So it can be, since it is downward to the left, no, so it can either be located somewhere here or somewhere here. Okay, so this location, okay, it can be checked or it can be proved, okay, where will be the correct as a location, okay, by solving for the moment, okay, of this system. Okay, so if your resultant or if the moment, okay, of all these forces, okay, about point O, let's say, is clockwise, okay, so your resultant must be it must be located here, okay, to produce a clockwise moment about point O. But if the moment of these forces, okay, about point O is counterclockwise, your resultant R should be located somewhere here so that it can produce counterclockwise moment. So it will depend to that, no, the location of your resultant will depend to that. So we will check that on our succeeding slide. So again, these are the tentative location of our resultant. So it can either be located somewhere here, okay, so that will be theta x from the horizontal, or here, somewhere here, okay, so this will be theta x also from the horizontal, okay. So to solve that, okay, or to confirm, okay, the location of our resultant R, we can take a moment about point O, okay. So we can solve for the moment, okay, of the component forces of our resultant R. So this will be the component forces. These are 20 Newton, 100 Newton, 60 Newton, and 100 Newton, and this 30 Newton force. So if we take their moment about point O, and if the moment about point O, their moment about point O is positive, meaning to say your moment, okay, is clockwise. So meaning to say your resultant R, its moment should be clockwise also. So it should be located somewhere here so that it can produce clockwise rotation about point O. But if the resulting moment, okay, of this component forces about point O is negative, meaning to say that moment is counterclockwise. So meaning to say your resultant should be placed somewhere here, okay, so that it can produce a counterclockwise moment about point O. Okay, so let's start solving for the moment of the component forces, okay, about point O. So let's start with okay, with this. So this is summation or moment at O is equal to summation of all the forces that have moment at O, and that will also be equal, okay, to the moment of the resultant, okay, about point O. So that will be RD. Now our assumption here is for clockwise moments or rotations, that will be positive. Okay, so let's start solving for the moment about point O. Okay, so let's start solving the moment of this 20 Newton force about point O. So we will put our component forces here, right? No, so if we put our component forces here for your 20 Newton force, your vertical force, okay, will pass through point O. Okay, so meaning to say it will have no moment about point O. So only the horizontal component of your 20 Newton force will have a moment about point O. So the horizontal component of this 20 Newton force is 20 cosine 30 degrees. Okay, so its moment arm about point O will be this perpendicular distance. So this will be 3 meters. No, so that will be 3 meters here. Okay, so it will rotate this way. So this rotation about point O is clockwise, right? So it will be positive here in our summation. Now, for our 100 Newton force here, okay, so if we put our components here, okay, so both of those component forces will have a moment about point O. So let's start with the horizontal component. So for the horizontal component of this force, that will be 100 cosine 45 degrees. Okay, and its moment arm about uh, of its rotation, okay, about point O. So that will be 3 meters also. So that will be 3 here. Okay, and its rotation about point O will be this way. Okay, so its rotation will be counterclockwise. That's why it will be negative here. Now, for its vertical component, that will be 100 sine 45 degrees. And its moment arm will be this perpendicular distance about point O. So this is 4 meters. So that will be 4 here. And its rotation about point O will be counterclockwise, right? It will rotate this way. So this is counterclockwise. Okay, that's why it's negative here. Now, for our 16 Newton force, okay, so its component or its moment about point O will be 60 Newton times its moment arm, which is this perpendicular distance. So this is 3. So this will be 60 times 3, and its rotation about point O will be this way. Oh, so it will rotate this way. So this is clockwise, right? That's why it's positive here. Now, for our 100 Newton force here, if we put our components here, okay, so your horizontal component here will pass through point O, meaning to say only your vertical component will have moment about point O. So the vertical component of this 100 Newton force is 100 sine 60 degrees. Okay, and its moment arm will be this perpendicular distance about point O, and this is 4 meters. Okay, so its rotation will be clockwise, right, about point O. Okay, so that's why it's positive here. Okay, so your 30 Newton force here is actually at point O. So meaning to say, it has no moment about point O. So it will just be not included, okay, in our summation here. So solving for the moment at O, okay, so let's input this in our calculator. So this will be 20 cosine 30 times 3 minus 100 cosine 45 times 3 minus 100 sine 45 times 4 plus 60 times 3 plus 100 sine 60 degrees times 4. So this will give you 83.40 Newton meters. So the answer here is positive. So meaning to say your moment about point O. Okay, so the moment of these component forces that make up the resultant. Okay, it's their moment about point O is clockwise. So if their moment about point O is clockwise, that will also be equal, okay, or equivalent to the rotation, okay, of the moment of the resultant. So that should also produce a clockwise moment about point O. So your resultant R, okay, we can confirm from here that it should be located somewhere here. Okay, so that it can produce a clockwise rotation, okay, I mean, okay, to be consistent here, okay, in the moment that we have. So, okay, so now that will be the moment about point O. Okay, so we are asked here again, we are asked to solve for the moment arm of the resultant from point O. Okay, so we are going to solve, okay, for that moment arm. We now know that the location of our resultant R is somewhere here. Okay, so this will be the right location of our resultant R. Now, our resultant, okay, so if we take its moment about point O, okay, so this will be that distance D. Okay, so that will be the moment arm. Okay, so we can actually equate this moment about point O and the moment of our resultant. Okay, so that will be R times D. And since we already have solved the magnitude of this resultant R, okay, so the unknown only will be this distance D. So we can do that to solve for distance D. So that will just be M sub O, or the moment at O is equal to R times D. So the moment at O is 83.40 Newton. And the resultant that we have solved from our previous computation, our R is 56.31. Okay, and our unknown here is distance D. So meaning to say, solving for distance D, that will just be 83.40, okay, divided by 56.31. So that will be uh, 1.48 meters. So this is the answer that we are looking for the second item that we are asked to solve here. So this will be 148 meter. Okay, so that will be the distance D of your resultant R from point O. Okay, so this moment at point O, this is actually not part of what are asked to us to solve. Okay, so I just boxed this, no, but this is not part of what are being asked to us to solve, no. So only the resultant, which are the magnitude, direction, and inclination, and the moment arm, no. So those are the items that we are asked to solve here in this problem. Now, for sample problem number 2, in a certain non-concurrent force system, it is found that the summation of f of x is equal to negative 80 Newton, the summation of Fy is equal to 160 Newton, and the summation of m sub o is equal to 480 Newton meter in a counterclockwise sense. Determine the point at which the resultant intersects at x-axis. So for this problem, okay, we have here summation of f of x. So this summation of f of x is actually the horizontal component of our resultant here. Okay, so this is negative 80 Newton. So meaning to say this horizontal component is directed to the left. No? And we have here summation Fy. Okay, so this summation Fy is actually the vertical component of the resultant. Okay, and since it is positive, meaning to say it is directed upward. Now, we also have here a moment at O, okay, and it is equal to 480 Newton meter, and this is counterclockwise. Okay, so that will be negative, no? And we are asked here to determine the point that which the resultant intersects at x-axis. Okay, so let's start solving this. Again, these are the given, okay, for this problem. So we have here Rx, okay, or the horizontal component of the resultant. We have here the Ry, or the vertical component of the resultant. And we have here moment about point O. Okay, so this will be the illustration, okay, of this problem. Okay, so our resultant will be directed this way because our Ry is upward, right? And from our Rx, that will be directed to the left. So meaning to say your resultant should be directed upward to the left. Okay, so also there's a given moment here, okay, at point O. So the given moment at point O is counterclockwise. So it will also satisfy that, okay, because this resultant R, if it is directed this way, okay, and if it will be rotated at point O, it will really produce a counterclockwise rotation. Okay, so it will produce this given. Okay, so from here, okay, we are asked here to solve for the distance, okay, or the point wherein this resultant, okay, will pass through, okay, the x-axis. So this is the x-axis, and the point where it will pass through is at this point. So we will solve for this distance ix. Okay, so this will be the item that we are going to solve for this problem. We are going to solve for ix. Now, to solve for ix, we can actually have two solutions here. Okay, so we are going to solve first using our solution 1. So for solution 1, we are going to use the given moment here. Okay, so the given moment here is negative 480 Newton meter, or 480 Newton meter counterclockwise. So we are going to use that, but we are going to take the moment of this resultant R. Okay, so by taking the moment of this resultant R, okay, so it should be equivalent to this moment, okay, which is moment at point O. Okay, so we are going to take the moment of the components, okay, of the components of this resultant R. So its components are Rx and Ry. So we are going to put our components here, okay, so that we can solve for Ix, so that we can involve Ix in our computation, okay. So what we're going to do here is take moment about point O. So moment at O is equal to summation of all the forces that have moment at point O. So our assumption here is clockwise for, or positive for clockwise rotation. So start solving for MO. So your MO will just be equal to ry times its moment arm, which is ix, and since it is counterclockwise, right, it will be counterclockwise, it will actually be negative, right? So your rx here, okay, since your rx will pass through the center of moment, which is point O, so it will have no moment about point O. So solving for this, your moment at O, okay, is given, no, that is negative 480 since that is counterclockwise. Okay, and for your ry, no, times ix, okay, so your ry is 160 newton. Okay, so that will be the value of your ry, and your ix is unknown. And since its rotation about point O is counterclockwise as well, so it will be negative here. Okay, so that negative will just be cancelled. So solving for the value of ix, that will just be 480 divide 160. Okay, so that will be 3 meters. So that will be your ix. So that is the point, okay, wherein your resultant or the resultant r will pass through the x-axis. So that will be 3 meters from the or from point O, no? So that will be our ix. Okay, so this will be the answer for this, okay, using solution 1. So we can also use solution 2. So for solution 2, okay, so we can actually solve this geometrically. Okay, so from here, we know that the perpendicular distance of r from point O will be this distance d. Okay, and there will be a formed triangle here actually, right? So from that formed triangle, we are going to solve for the value of ix. Okay, so in this triangle, okay, the sides that we need here, okay, to solve is this distance d. Okay, so to solve for this distance d, okay, we just have to also use this moment at O, okay, and we also have to solve for the resultant r. Okay, so to solve for the resultant r, it will just be square root of rx squared plus ry squared, wherein your rx is 80 newton and your ry is 160 newton upward. Now, so solving for your r, it will just be 178.89 newton, and its direction nga is upward to the left. So again, let's input that in our calculator. That will be square root of negative 80, no, for our rx. So that will be negative 80 squared plus 160 squared. So that will be 80 times square root of 5, or 178.89 Newton. So that will be the magnitude of our resultant. Now, to solve for this distance d, okay, so again, we will use this moment at O. Okay, so your moment at O will just be equal also to the moment of this resultant R. Okay, so the moment at point O, okay, that is negative 480 since that is counterclockwise, okay, and that is also equivalent to RD, wherein your R is 178.89, okay, and your moment arm here will be this distance D, and since the rotation of your resultant R about point O will be counterclockwise, right, so it will also be negative here. So now, solving for distance D, okay, or perpendicular distance d, or the moment arm, okay, so that will just be 480 divided by 178.89. So the negative here will just be cancelled. Okay, so the answer will be 2.6832. No, so we will use a lot of decimal places here, no, so that our, since this is not yet the final answer, no, so so that the consistency, okay, or the desired accuracy, okay, of our solution will be met, no. So we will use at least 5 or 4, no, 4 decimal places here, okay, for the accuracy of our answer. Okay, so since we have already solved for distance d, okay, to solve for ix, we also need to solve for theta x. Okay, so for theta x, okay, as we know, this is the inclination, okay, of this resultant are about the horizontal, okay, or from the horizontal. Okay, so we can solve this theta x by using tangent theta x equal to ry over rx. So your ry and rx are given. So we can use that. So to solve for theta x, it will just be arctangent of ry over rx. Okay, so let's input that in our calculator. That will just be arctan of ry. Your ry is 160 newton and your rx is 80 newton. Okay, so that will give you 63.435 degrees. Okay, so this will be our theta x. Okay, so this will be our theta x. So we have already solved for distance d for theta x. Okay, and now from the triangle, so if we take this triangle, no, so we can draw it this way. So our perpendicular distance d, of course, this is perpendicular here, right? So this is perpendicular here. Okay, meaning to say that is 90 degrees, right? So from this triangle, okay, if our theta is here, okay, so the side that is opposite to our theta will be the opposite side. So we can apply SOHCAHTOA here since our angle is a right triangle, right? So again, our theta x is here. So the side opposite to that theta x will be the opposite side. Okay, and the side adjacent to that theta x, okay, actually this is the adjacent side. Okay, and this is the hypotenuse. No, your ix will be the hypotenuse. Your distance d will be the opposite side, and your ix will be the hypotenuse. So in SOHCAHTOA, what can we use? SOHCAHTOA, the available is opposite and hypotenuse. So we can use sine, so opposite over hypotenuse. So using sine theta, so that will just be d over ix. Okay, so sine theta x equal to d over ix, wherein we have already solved for theta x and we have already solved for distance d or perpendicular distance d. So we can now solve for ix. Okay, so substituting the values of the quantities that we have solved. So this is sine of 63.435 degrees equal to 2.6832 over ix. So solving for ix, okay, so that will just be, we will just cross multiply this, no? So we can interchange ix and sine 63.435 degrees here so that we can solve for ix. So that will just be 2.6832 over sine of 63. So let's input in our calculator 63.435 degrees. So that will be 3 meters as well, right? So the answer will be 3 meters as well. So of course, your solution 1 and solution 2 should give you the same answer. So either of these two solutions you can apply, no? So this will now be the answer for this problem, 3 meters. So let's proceed now to sample problem number 3. Determine the resultant of the three forces acting on the dam and locate its intersection with the base AB. For good design, this intersection should occur within the middle third of the base. Does it? Okay. So for this problem, we have here this dam. Okay, so this dam has this forces P, which is 10,000 Newton. We also have force W here, which is 24,000 Newton. And we have here force F, which is 6,000 Newton. So these forces, okay, are actually non-concurrent. Okay, since these forces, okay, don't meet at a common point. So therefore, this is a non-concurrent force system. So we are asked here to solve for the resultant. Okay, so we will solve for its resultant. And also, we should give also the location, okay, of its intersection with the base AB. So this is base AB. So we will solve here, okay, if where is the location, okay, where it will intersect, okay, the resultant where it will intersect our base AB. So for good design, this intersection should occur within the middle third. So what will be the middle third of the base? So our base here is 18 meters. Okay, so the middle third, okay, of your of this base, which is 18 meters, should occur, okay, between 6 meters to 12 meters, right? Okay, so if you divide 18 meters by 3, that will be 6. Okay, so meaning to say your middle third or within the middle third, that should occur, okay, between 6 meters to 12 meters, right? So within that interval. Okay, so if our resultant, okay, passes through, okay, that interval, no, from 6 meters to 12 meters, meaning to say this dam is good design. Okay, so we will start solving this, okay, this problem. Again, for this problem, we are asked to solve for the resultant. Again, that should include the magnitude of the resultant, the direction, and the inclination. Okay, now we are also asked here to solve for the location, okay, of the intersection of the resultant with the base AB. So we will determine, okay, where will our resultant R, okay, will pass through here in our base AB. Also, we are asked here if the resultant will intersect at middle third of the base. So again, the middle third of the base, okay, will be from 6 meters to 12 meters. Since this is 18 meters, that will be divided by 3. That will be 6, and then plus 6, that will be 12, and then plus 6, that will be 18. Okay, so meaning to say, your middle third should be within 6 meters to 12 meters. So that will be your middle third. Okay, so our resultant, okay, should pass through that middle third. Okay, it should pass through 6 meters to 12 meters, okay, from in our base AB, so that we can say that it is good design. Okay, so we will confirm this, okay, in our computations. Okay, so for now, we have to solve first for our resultant. So we have to solve for Rx and Ry. So to solve for Rx and Ry, okay, so again, this is our DAM. Okay, so for our horizontal component of the resultant, that will be Rx, that will just be equivalent to the summation of all the horizontal components, okay, of all the forces in our system. Okay, so these are the forces in our system. Okay, so the forces that have a horizontal component, okay, are this 10,000 Newton force and this 6,000 Newton force. For this 6,000 Newton force, this is actually perpendicular, okay, to this incline. Okay, so if it is perpendicular to this incline, okay, if this is 60 degrees, if the incline is 60 degrees, if we put here a vertical axis, okay, so the angle, okay, from the vertical axis to this force, okay, it will be equal to this inclination, okay, to this 60 degrees. So this will also be 60 degrees here. Okay, so from here, we can now start solving for Rx. So for your Rx, that will just be again, the summation of all the horizontal component, okay, of the forces. So let's start here with 10,000 Newton force. So since this is already horizontal, also this will be directly included in our summation. So since this is directed to the right, it will be positive here, okay, positive 10,000. And okay, let's proceed now here in this 6,000 Newton force. Okay, so since this is inclined, no, so there will be a horizontal component. So its horizontal component, okay, so since our angle here is here, okay, so what we need here will be the opposite side of the triangle that will be formed here, right? And our angle is here. So the opposite side is here, right? So what we need here to solve for the vertical, or the horizontal rather, the horizontal component of this 6,000 Newton force will be 6,000 sine. So since this is the opposite side of this triangle formed here, our angle here is 60 degrees and it is here. So what we need is this side of that triangle, and that will be the opposite side of the triangle, right? So that will be 6,000 sine 60 degrees. Okay, and since our force F, okay, this force is directed to the left, it will be negative here. So we can now solve for Rx. So let's input this in our calculator. This will be 10,000 minus 6,000 sine 60. So the answer for this will be 4,803.8 Newton. Okay, so since this is positive, so meaning to say the horizontal component of the resultant will be directed to the right. Okay, so that will be our Rx. Now let's proceed to our Ry. So for our Ry, that will just be the summation of the vertical component of the forces, okay, in our system. Okay, so the forces that have vertical components here are this 24,000 Newton force, okay, and this 6,000 Newton force. So starting to sum this up, okay, so for your Ry, so your 24,000 Newton force here, since this is already vertical, so this will just be directly included here. And since it is directed downward, it will be negative here in our summation. Now for our 6,000 Newton force, so the vertical component of this 6,000 Newton force, since our angle is here, so the vertical component is here, right? in this triangle form. So this, in the triangle form, this will be the adjacent side since the angle is here, right? So the adjacent side here, so what we need to do is cosine, or use, no, is cosine, since the side that we need here is adjacent, so adjacent. Okay, so we need here cosine, okay, to solve for the vertical component of the 6,000 Newton. Again, since our angle is here. Okay, so that will be 6,000 cosine 60 degrees. So that will be the vertical component of that of this force, no? So since this is directed downward, right? This is downward. So this will be negative here in our summation. So solving for Ry, so let's input this in our calculator. This will be negative 24,000 minus 6,000 cosine 60. So this will be negative 27,000. Okay, so our answer here is negative. Therefore, our Ry, or the vertical component of the resultant, will be directed downward. That will be 27,000 Newton downward. So we now know the direction of our resultant, that will be downward to the right. Okay, so it will be directed like this, downward to the right, downward to the right, right? So solving for the value of r, okay, or the magnitude of r, that will just be square root of rx squared plus ry squared. Okay, so let's input the values in our calculator. So that will just be square root of 483.8 squared plus 27,000 Newton squared. So that will be 27,424 Newton. So that will be the magnitude of the resultant, and its direction again will be downward to the right. Okay, so that will be our answer for that, no, for the resultant. And also we need to solve for the inclination, or the theta x. So that will just be arctangent of ry over rx. So let's input that in our calculator. That will just be arctan of ry. Our ry is 27,000 and our rx is 4803.8. So that will give you 79.912 degrees. So that will be our theta x. So it is also part, okay, of our answer in resultant, no? So this will be the answers: the magnitude, the direction, and the inclination, or the theta x. Okay, so we will now proceed to the next item, okay, which is the location of the intersection of the resultant with the base AB. So let's proceed. Okay, so again, for the second item, we have to solve for the location of the intersection of the resultant with base AB. Okay, so we are going to assume the location, okay, of our resultant R. Let's say it will pass through, okay, this base AB this way. Okay, but we are sure that the direction of our resultant R is downward to the right. So we are sure here, no, since we have already solved that, no, in our previous slide. Okay, so what we are not sure here yet, okay, is the point, okay, where it will pass through base AB. Okay, we are not sure yet. So we will assume that it will pass through this way. Okay, so let's say that this resultant R, okay, the point where it passed through or it passes through base AB will be at this point. Okay, so from this point to point B, let's say that that is distance x. Okay, so now for our solution here, okay, to solve for this x, okay, so we need x, no, to solve for this x. So this will be the location of the intersection of the resultant with base AB. Okay, so this will be the item that we have to solve, no, this distance x. Okay, so to solve that, okay, we can take the moment, okay, of our resultant R, okay, by taking the moment of its component forces. Okay, so its component forces, so let's put the component forces, or the horizontal or vertical component of our resultant R, let's put at this point. Because if we put at this point, okay, only Ry will have a moment at point B. Okay, and the moment arm of this Ry, no, we can incorporate X here because that will be the moment R of your, or moment arm, okay, of your Ry. Okay, so the moment of this vertical component, horizontal and vertical component, okay, of this resultant are about point B, that will also be equal to the moment, okay, of this component forces, this 6,000 Newton, 24,000 Newton, and 10,000 Newton force. Okay, so these are the component forces also of the resultant R because these are the forces that make up, okay, the resultant R. Okay, so if we take the moment of these forces, okay, about point B, it should be equal, okay, to the moment also of the horizontal and vertical component of your resultant R. Okay, so let's start solving this. Okay, so we will take moment at point B. Okay, so we will take moment at point B, so that will just be equal to the summation of forces that have moment at point B. Okay, that will also be equal to the moment of the resultant about point B, and also that will be equal to the summation of the moment of the component forces of the resultant, or the summation of the horizontal and vertical component of the resultant about that same point, which is point B. So we will start solving this by solving first for the moment at B. So for the moment at B, so we will solve the moment at B using the component forces 10,000 Newton, 24,000 Newton, and 6,000 Newton. No, so for 10,000 Newton, so its moment about point B will be 10,000 times 6 meters, since the moment arm will be 6 meters, right? And it will have clockwise rotation about point B, right? So it will be positive here. Now, for this 24,000 rather, 24,000 Newton force, okay, so its moment about point B, okay, so its moment arm will be 18 meters minus 7 meters. So this will be that distance, right? Okay, this distance, no, that will be the moment arm. Again, that will be 18 meters minus 7 meters. So that will be 11. So 24,000 times 11, okay, and its rotation about point B, it will be counterclockwise, right? So that will be negative here. Okay, now for your 6,000 Newton force, okay, since our 6,000 Newton force, okay, has a perpendicular distance here, no, from point B, this is actually perpendicular distance, right? Since this force F, this 6,000 Newton force is perpendicular to this incline. So this 4 meter will be a perpendicular distance. So that will be the moment arm already if we take the moment of this 6,000 Newton force about point B. Okay, so that will be 6,000 times 4, okay, and its rotation about point B will be counterclockwise. That's why it will be negative here in our summation. Okay, so solving for moment at B, okay, so that will be 10,000 times 6 minus 24,000, okay, times 11 times 4, minus 6,000 times 4. No, so your moment at B will be negative 228,000 Newton meter. Since the moment here is negative, okay, meaning to say our moment, okay, the moment of these forces about point B is counterclockwise. Okay, so that's why it's negative here. And it will also satisfy, okay, our resultant, right? The moment of our resultant R about point B. Because if your resultant R will rotate about point B, it will also produce counterclockwise moment. Okay, which satisfies, okay, the moment that we have solved here. Okay, the moment at B. Okay, now since we have here already the moment at B, okay, so we can have two solutions here nga, no, to solve for the value of what we need here, which is this distance x, no. So for our solution 1, we will take the moment, okay, of the component forces or the horizontal and vertical component of our resultant R. We will take their moment about point B, and we will equate that, okay, to the moment, okay, of these forces that we have solved here, which is to 228,000 Newton meter. So we will equate that. Okay, so again, moment at B, so that will just be equal to the moment also of the vertical and horizontal component of the resultant. Okay, so our moment is negative 228,000 at point B, no? So that's the value that we have solved. And since it is counterclockwise, it will be negative nga here, no? So from the horizontal and vertical component of the resultant, so your Rx will pass through point B, meaning to say it will have no moment about point B. So only Ry will have a moment about point B, and its moment arm will be X, no? And that is the item that we are solving here. Okay, and we have already solved also for Ry, right? Okay, from our previous slide, we have already solved for Ry. Okay, so its rotation, okay, your Ry, the rotation of your Ry about point B, okay, will be counterclockwise, right? It will rotate this way, it will rotate this way, so that is counterclockwise. That's why it is negative also here. So we, since we have already solved for Ry, that is 27,000, we can now solve for the value of x. So the negative here will just be canceled. So 228,000 divided by 27,000. So that will give you 76/9 or 8.44 meter from point B. So that will be the x distance here, no? So that will be the value from point B, or the distance or the location of our resultant. Okay, from point B, okay? Or that will be the location of the intersection, rather, of the intersection of our resultant R from point B, no? So that will be 8.44 meter from point B. Now, we also have a question here. If the location of your resultant, okay, if its intersection, no, in the base AB will pass through the middle third, no? So our x, okay, this x, okay, it should be from, again, it should be from within, rather, it should be within 6 meters to 12 meters, right? To say that it is found in middle third. But since our x here is 8.44 meters, that satisfies that, right? That it should intersect from 6 meters to um, 12 meters, right? And since this is 8.44, it satisfies that. So meaning to say, okay, meaning to say, since it satisfies this, no, that uh, our x is within 6 meters to 12 meters. So meaning to say, okay, your x, no, or the intersection of the resultant R with base AB intersects middle third of base AB. Okay, and therefore the dam is a good design. Okay, because it passes through the middle third nga, no. So that will be the answer for this using solution 1. Okay, so we will also solve this using solution 2 in our succeeding slide. Okay, so now for our solution 2, okay, we are going to use the moment arm of our resultant, no, about point B. So that moment arm is this perpendicular distance D. No, so if we put our distance D, or if our distance D is located somewhere here, okay, it can form a triangle here. So the form triangle here, if we blow that up, no, so this will be that triangle, no. So this is the distance D. So of course this is perpendicular here. So this will be actually a right triangle, right? And our theta x, okay, so it will be located here from the horizontal, right? So your theta x, it can be solved by using arctangent Ry over Rx. Since we have already solved for Ry and Rx, we can solve for theta x, no? And also, we can also solve for distance D, right? Since we already solved for our moment, okay, at B, okay? And since we already have the magnitude of our resultant R, okay, so if we apply Varignon's theorem to that, no, that the moment at point B is also equal to the moment of the resultant, okay? Okay, wherein the moment of that resultant will just be R times D, so we can solve for distance D. So after solving for distance D and theta x, we can now solve for this x, no? So this is what we need, this distance x, no? So from this right triangle, we can actually use SOHCAHTOA, no? So whatever is applicable from that, no? So we will first solve for distance D, no? So our theta x, we have already solved that, no? So for our distance D, so again, that will just be moment at B is equal to the moment of the resultant about that same point, which is point B. So that will just be RD. So again, our assumption here for positive is clockwise rotation. So our moment at B, we have already solved that. That is negative 228,000. Okay, and our resultant R, we have already solved that also. That is 27,424. But since our moment at B nga is negative, no, right? That is negative since the moment is counterclockwise. No, and also for our resultant R, its moment about point B. Okay, if we rotate this about point B, it will be counterclockwise as well. So this will also be negative here. Okay, so our moment arm here is distance D, so this will be that distance D. So we can actually solve directly distance D from here, right? So the negative sign will just be canceled. So this will be 228,000 divided by 27,424. So this will give you 8.3139 meters, no? So that will be the distance D. Now again, we have already solved for theta x from our previous slide. So that will be 79.912 degrees. Okay, so from here, since we already have theta x and distance d, we can now solve for x using SOHCAHTOA. Since this is a right triangle, we can use SOHCAHTOA. So our distance d here, this is actually the opposite side of the triangle, right? Since this is the side opposite to our theta x. Okay, and this x, okay, so since this is the longest side of this triangle, this is the hypotenuse. Okay, so the available data here are opposite side, hypotenuse, and theta x. So meaning to say what we can use from SOHCAHTOA is so, since that is the function that has opposite and hypotenuse, right? So opposite over hypotenuse. So we can use sine theta x is equal to the opposite side, which is distance d, this perpendicular distance d, over the hypotenuse, which is x. So since we already have theta x, which is 79.912 degrees, and we have already solved the distance d, which is 8.3139, we can now solve for x. So cross multiplying this, we can interchange x and sine 79.912 to solve for x. So that will just be, let's input in our calculator, that will be 8.3139 over sine of 79.912 degrees. So that will be 8.4444 meter from point B. So that will be 8.44 meter from point B. So this will be what we are looking for. No, this will be the location of the intersection of the resultant with the base AB. Again, there is a follow-up question here. If our resultant intersect at middle third of the base, no, so again, the middle third of the base should your resultant should pass through within 6 meters to 12 meters. So since our x here is 8.44 meters, it satisfies that, right? It satisfies that interval, no? So therefore, your x, no, or the intersection of the resultant with the base AB intersects the middle third of that base, no? So therefore, the dam is a good design. Okay, so that is also the follow-up question if the design is good, right? So therefore, okay, the design of the dam is good. So this will now be the answers for this problem using solution 2. And this is also the same answers, okay, with the answers that we had in solution 1. Okay, so this will be the answers now for this problem. Now, let's proceed to sample problem number 4. The force system shown consists of the couple C and 4 forces. If the resultant of this system is a 500-pound-inch counterclockwise couple, determine P, Q, and C. Okay, so our situation here is that this force system has 4 forces. So these are the forces that are mentioned here. Okay, and also there is a couple C. Okay, so this is the couple C. So this couple C is actually a component couple here, no? So this is part of this force system, no? Okay, so there's also a given here, no, that the resultant of this system is a couple. Okay, so we have already discussed in our topic, no, about couple. Okay, that if the resultant, or if the resultant of the system is a couple, meaning to say the resultant force is zero, right? So that's the concept. Okay, if the resultant of the system is a couple, again the resultant force is zero. Okay, so we are asked here to determine P, Q, and C. So from that, no, from that given, okay, we can now start solving. Okay, so again, our given, okay, here is the resultant of this force system is a couple. Therefore, the resultant force of this system is zero. Okay, and if the resultant, okay, of this system is zero, meaning to say its Rx and Ry are also both equal to zero. Okay, so we can use this data that Rx equal to 0 and Ry is equal to 0. Okay, and also again, our couple here or the resultant here is a couple, okay, which is negative 500 pound-inch, no, since it is counterclockwise. So we can use this, no, when we take moment, okay, at any point in this system, because a couple, okay, as we have already discussed also in our discussion about couple, that a couple, okay, is independent of the center of moment. Okay, and independent and constant, no, at the same time. So, meaning to say, even if we take moment at any point, okay, in this system, okay, that couple, okay, will be the same, will be the same magnitude and direction, no. So we can use that, no, given later on. So again, we are asked here to solve for forces P, unknown force P, unknown force Q, and the unknown couple C. So this couple is different from this couple here, ha? So this couple is a component couple here. So this is part of the system. Okay, so we will start solving now. Okay, so for our solution to use, no, we are going to use, no, the given here, the data that we have established here, that Rx equal to 0, no. So we will use that here. So we can use this equation that Rx is equal to the summation of the horizontal components of the forces, okay, in our system. Okay, so our Rx, again, that will be automatically 0. Okay, so that will automatically be equal to 0. And let's start summing up all the horizontal component of the forces. So let's start with force Q. So for this force Q, okay, so there is a given slope triangle here. Okay, so our slope triangle here is 5, 12. So solving for the hypotenuse of the slope triangle, that will just be square root of 5 squared plus 12 squared. That will be 13. So that will be the hypotenuse side, okay, of our slope triangle. And also here, we also have a slope triangle here, 3 and 4. The rise is 3 and the run is 4. So we can solve for the hypotenuse of that slope triangle. That will just be square root of 3 squared plus 4 squared, and that will be 5. No, so from that, no, so again, we will start with force Q. So this is our force Q. So its horizontal component will just be Q times the side that is parallel, okay, to that component, which is horizontal component, that is 12. No, so that will be 12 over the hypotenuse, which is 13. So that will be Q times 12 over 13, okay? And since it is directed to the left, okay, this force Q is directed to the left, that will be negative here. So this is summation of forces, of component forces, okay, or horizontal component of forces, no. So there will be no moment arm here, okay, just to make sure that you will not get confused here, no. So we will not have moment arm here. This is summation of forces. Okay, so this will be the horizontal component of force Q. Now let's proceed to the 80-pound force. So this is already horizontal, so we will directly involve that in our summation. Since it is directed to the right, it will be positive here. And also, we will proceed now for force P. Okay, so the horizontal component of force P will be P times the side in the slope triangle that is parallel to the component that we are solving, which is horizontal, no, horizontal component. So this will be the side parallel to that. So that will be 4. So P times 4 over the hypotenuse, which is 5. So that will be the horizontal component of P. Now, this 20-pound force, this is actually vertical. So it will not be included in our summation here. And also, your couple here, it will not be included in this summation, since this is summation of forces. No, so this is not summation of moment. No, so this couple C, it will be included when we sum up moment, since your couple is a moment. Okay, this couple is a moment, right? So it will not be included in summation of forces, no, since that is not a force, that is a couple. So we can now generate our equation 1 from here, no? So this will be our equation 1. Now, we can also use Ry is equal to 0. So we can use Ry is equal to summation of all the vertical component of the forces in our system. So Ry will be automatically 0. Okay, so we will start summing up the vertical components. We will start here with Q. Okay, so the vertical component of Q will just be Q times the side in the slope triangle that is parallel to the component that we are solving, which is vertical. So this will be that side, that will be 5. So it will be multiplied by 5 over 13. No? 13 is the hypotenuse. No? So this will now be the vertical component, okay, of force Q. No? So since it is directed downward, okay, so it will be negative here. Okay, so also for your 20-pound force, no, so since this is already vertical, okay, so this will be directly included in our summation, and since it is downward, it will be negative here, so that will be negative 20. Now, for our force P, okay, so its vertical component will be P times the side in the slope triangle that is parallel to that component that we are solving, which is vertical. So the side that is parallel to that is this 3, no? This side that is 3. So that will be P times 3 over the hypotenuse, which is 5. Okay, and since this force P is directed upward, it will be positive here. Okay, so this will now be the second equation, okay, for this solution, no? So from the equations 1 and equation 2 that we have generated, okay, since these are two equations and we have two unknowns here, P and Q, okay, so we can actually solve for P and Q by solving simultaneously these two equations. Okay, so we can solve this by elimination, or we can solve this by substitution, no? So solving equation 1 and equation 2. So what we're going to do here is, let's say we will generate the value of Q, no? Okay, from equation 2. So we will solve for the value of Q, of the unknown quantity Q. So that will be, we will just transpose Q to the other side, no, so that it will become positive, and divide both sides by 13 over 5, so that only Q will remain in the left side. So this will be multiplied by 13 over 5, right? So this will be negative 20 plus P times 3 over 5 times quantity, no, quantity times 13 over 5. Okay, so this will be the value of Q. Now this Q, okay, we can now substitute this to our equation 1. So substituting this to our equation 1, okay, so this will be 0. So your Q is negative. This is negative here, no? And your Q is negative 20 plus P times 3 over 5, quantity 13 over 5. Okay, so this is also multiplied by 12 over 13. Okay, so don't get confused. We just substitute the value of Q here. Okay, and then plus 80 plus P over, or P times 4 over 5. Okay, so from here, only P is the unknown. So we can solve for P, no, from here. Okay, so solving for P, it will give you 200 pounds. Now, if you have already solved for the value of P, okay, we can now substitute that value to either equation 1 or equation 2, okay, and you can now solve for the value of Q. So our Q here is 260 pounds. So this will be the answers for P and Q. So we have already answered the two of the items that we are asked to solve, no? So there will be remaining item here, which is the couple C, no? So we have to solve for this couple C. So to solve for this couple C, okay, so this is a component couple, ha? So this is part of the system. So we can use, okay, also the resultant couple, okay, that is given here, okay, which is 500 pounds each. So using that, okay, so again, our concept for couple is when you take moment at any point here in this system, okay, it will be the same moment effect, okay? So we can use our given couple, resultant couple here. So, okay, so we will take moment at point O. Okay, so the moment at point O, okay, it will be equal to this resultant couple. Okay, so this is 500 pound inch and this is counterclockwise. So this will be negative, and that will also be equivalent, okay, to the moment, okay, of all these component forces. Okay, of the moment of these component forces that make up the resultant. So we will take their moment about point O as well. Okay, so that will be, okay, for moment at O, that will be the resultant moment or the resultant couple, which is 500. Since it is counterclockwise, it will be negative here. So we will take the moment of all the forces here about point O. So for force Q, if we put our component forces here, okay, so only the horizontal component of force Q will have a moment about point O, since vertical its vertical component will pass through point O, right? So its horizontal component again is Q times 12 over 13. Okay, and its moment arm about point O will be 1, 2, 3, 4, 5, 6. So this is in inch, no? Every square here is 1 inch, no? Or the side of the square here is 1 inch, no? So this will be 1, 2, 3, 4, 5, 6 inches, no? So this will be 6 here. Okay, that will be the moment arm. Now, the rotation of the horizontal component of Q about point O will be counterclockwise. That's why it will be negative here. Now, for 20, no, we will take the moment first of 80 pound. No? So for 80-pound force, its moment about point O will be 80 times its moment arm, which is 2. So that will be 80 times 2, and its rotation about point O will be clockwise. That's why it will be positive here. Now, for the 20-pound force here, its moment about point O will be 20 times its moment arm, which will be this perpendicular distance, right? This is 3 inches. No, so that will be 20 times 3. And its rotation about point O will be clockwise. That's why it will be positive here. Okay, now for your force P, so this will be our force P. Okay, so for our force P, no, so if we put our component forces here at this point, no, so only the vertical component, okay, will have moment about point O, since the horizontal component will pass through point O. So for the vertical component of force P, that will just be P times 3 over 5, and its moment arm will be 1, 2, 3, 4, 5, 6. So that will be 6 here, and its rotation about point O will be counterclockwise, right? The vertical component of P, that will be counterclockwise. That's why it will be negative here. Okay, now, we also have here a component couple. So this will be included in the summation of moments here. Okay, so our couple here is clockwise, right? This is clockwise. So since this is clockwise, this will be positive here. So this will be plus C. Oh, so this is already a couple, ha? So there will be no moment arm for a couple because that is already a moment. Okay, so that will directly be the quantity, no, the unknown quantity, that will be C, no, that will be included here in our summation. Okay, so since we have already solved for the value of Q and P, we can substitute these values, no. So for Q, that will be 260, and for P, or rather for P, that is 200. For Q, that will be 260, no. So the only unknown here now is C, right? So solving for C, okay, so solving for C, okay, that will just be, if you input that in your calculator, that will give you 1,440. So the unit here is pound inch, no? Since the forces here is pound and the distance that we use here is inch, no? So don't forget, okay, to include this unit, okay, to include the right unit. So you really have to check always, okay, the given, no, in the problem, no. So this is pound inch, because if your the unit that you give to your answer is wrong unit, no, your answer will be wrong. So this will now be the value of your couple C. And since positive, the answer here is positive, no, so it really satisfies that our couple C is clockwise, no. So this will now be the value or the answer for C, no. Yeah, so this will now be the answers for these problems for P, Q, and C. So that concludes our discussion. I hope you learn, and I hope that you attain the learning outcomes for this topic. And also, class, I just want to remind you that you will reap a harvest, okay, at the end of this if you don't give up. Okay, so let us persevere and let us diligently study this. Okay, because you know what, class? Your efforts are not in vain. Okay, God bless you, class. God bless. Bye. Keep safe.